let's talk about this homework problem. Suppose we put two thumbtacks in a piece of paper at -3, 0 and 3, 0. Then take a string of length 8 centimeters, tie it around each thumbtack, and use a pencil point, keep the string taut, and move the pencil around, keeping the string taut. So the distance from one tack to the pencil point to the other tack is always 8 centimeters. Write an implicit equation that describes the situation, which we can rephrase as the distance from xy to the first tack plus the distance from xy to the second tack is 8 centimeters. So let's shift to doing this on paper. Alright, I didn't have thumbtacks handy, but I had some old school Legos, so let's use that. And this string is tied behind the back, so its total length isn't going to change. We can basically ignore the amount of string from this hole to that hole running across the back. And the distances aren't exactly 3 centimeters or 8 centimeters, but the same idea applies. So I'm going to kind of grab my string with the pencil point and make it taut and put this down. And then I'm going to trace around, keeping that string taut. And what geometric shape am I getting there? And presumably I could do the same thing below. So what would you call that? Let's mark our positions here. Does that look a lot like an ellipse? I think that string got a little stuck on something here. It should be symmetric, top bottom. So it looks kind of like an ellipse. Let's think about it in more detail. We said this was -3, 0 or something like it. This was 3, 0, and we'll pick some kind of point and call it xy. That's actually an important math move to say, I want to think about points on this shape. Let me give them a name, even though I don't know the value of any of them. I'll call them xy, and then I'll think about what's the distance from xy to this location, what's the distance from xy to that location. So I had something like that, and something like that. And let's call this D1. Let's call this D2, D for distance. So then what we're saying is that D1 plus D2 has to equal 8 as it was in the problem. So then the question is, what is D1? What's a formula for D1? Well, it's the distance between x, y and -3, 0. Remember the distance formula? Square root of the difference of the x's squared plus the difference of the y's squared. So big old square root, x minus -3 squared, that's the difference of the x values of my 2 points, minus y minus 0 squared, that square root. And then d2 is the same basic idea, but with just 3 instead of -3. And then we want all points where this is true, and we did it physically. Let's go try it in Desmos. All right, here we are. I set a slider for a, the distance of each of these points from the origin, and I set up my distance formula from point x, y to -a, 0, from x, y to a, 0. And here I'm computing the total distance from any particular point to those 2 points, and I've got a movable point here. And you can see this is computing the total distance. So here I'm not keeping that string taut at 8 centimeters. I'm just moving around and saying, okay, somewhere, let's see, I'll try to get that near 8. Somewhere on this arc, that number is staying somewhat near 8. But instead of kind of moving and guessing that number, trying to keep that near 8, I can say, just show me all points where D1 plus D2 is equal to 8, and it does it. And I guess we were pretty close. And if this point is farther away, then its total distance is more than 8. If it's closer to those points, then it's less than 8. This lets us do some fun things. We can say not just 8, but 1, 2, ... 50. And it shows us all the points where D1 plus D2 is equal to 7, and 8, and 9, and 10, etc. So that's a whole family of ellipses. Now you might be thinking, you've seen a formula for an ellipse before, and it doesn't look like this big old square root plus that big old square root equals some constant. Let's turn this off for a sec and go add a new formula. Well, you might remember like x squared plus y squared equals 1. That's the unit circle, or equals like 3 squared, that's a circle with radius 3. So that's a circle. How about an ellipse? You might remember you can scale x. So you can do like x over, let's do 5 squared plus y divided by, I don't know, 7 squared equals 3 squared or something. And that gave us an ellipse. We can change the scaling here. Let's use 11 and 5 to make it an ellipse the other way. So how does this formula with the simple scaled x squared plus scaled y squared equal something? That's kind of the classic formula for an ellipse. It's much more elegant than this. How do you get from this formula with square roots all everywhere to this formula? It turns out it involves a lot of algebra. You have to basically move one of these to the other side, square both sides to get rid of the square roots, but there's still a square root because you've had to FOIL, and then you move stuff again and square again to get rid of more square roots, and it's just a big pain in the neck, but it does eventually boil down to this. The other question we asked in the homework is, what if the difference of the distances was, let's bring that up. So ignoring the string analogy, what if the difference of the distances is always some particular number? Well, we can go change that here and just put a minus there, and put a minus here, and change that to a 2, and oh, forgot to plot it. There we go. So now instead of an ellipse, we're getting this shape. Any guesses as to what that is? It kind of looks like a parabola, but it's actually a hyperbola. And if we change that 2 to something like 1, 2, ... 10, we get a whole family of hyperbolas. If we had done the subtraction the other way, so if we put a minus here and a plus there, we get hyperbolas on the other side. All right, so that's conic sections and implicit functions, because this formula is an implicit function for y and x, so that's relevant to implicit differentiation.